Hey everyone, this is an extra video to review basically all of chapter 11 that we've seen, and then also as sort of like a reflection from exam 2, just to touch base on improper integrals from section 7.8. So this problem 1 will be 7.8. One of the main things that I saw on your exam 2 was that just because an integral is improper does not necessarily mean that it diverges. Okay, so these are two totally different concepts. In fact, an improper integral has the possibility to diverge or converge, and the following three examples are all examples of improper integrals that end up converging. The other issue that we've when I say we, Dr. Hamidine, I noticed on exam 2 was that the recognition of an improper integral is sometimes not there. So we want you to notice in each of these examples why an integral is improper, and then deal with it so that you can actually find what it converges to in a kosher way, okay? So this integral from 0 to 2 of, I'll rewrite it as x to the minus 1/3, it's improper. And the reason it's improper is because there is a discontinuity of our function that we're integrating. There's a discontinuity of our 1 over x to the 1/3 at one of the x values in our limit, in our limits of integration, which is the closed interval from 0 to 2. So the limits of integration are the closed interval from 0 to 2. Anytime there's a problem spot, whether it be at the endpoints or within the interval, you've got an improper integral. Okay, so how do we fix this? Well, we have to replace the bad part of the integral with what I'm calling a dummy variable. So we're going to replace 0 with a, and because we are coming at 0 from the right hand side within this interval, we are going to take the limit of our dummy variable as it goes to 0 from the right. All right, so we've made this replacement, and now the reason we had to do that was because we cannot apply the fundamental theorem of calculus to a function that's not continuous on its interval of integration. So a lot of you did not do this limit replacement, and basically, I'm going to erase some stuff. You basically just said, this is equal to this from 0 to 2. And this is not allowed, okay? So this is the fundamental theorem of calculus being applied to an improper integral, and you cannot do that. So let me go back, get everything back in there that I originally had. All right, so you have to do this limit replacement, even if it seems like extra work that you don't have to do. You do need to do it. All right, so this is then the limit as a goes to 0 from the right, again, and we plug in our limits. Our first limit is 2. Our second limit is some number a, that's between 0 and 2, and we take the limit as a goes to 0 from the right, which becomes 0 in that second term. And then we are left with this finite value. Okay, so this finite value is what our integral converges to. And because this limit that we created here, because this limit exists, we can say that our original integral is equal to that limit, which is equal to this finite value. Okay, so there's a lot going on here, but hopefully that gives you an example of something that is improper, but it converges. to a finite value. Okay, let's do another one. Okay, so this next one, remember, if there's a discontinuity, discontinuities can be due to lack of definition at a certain x value. So notice that this is improper because your function, x, natural log of x, isn't even defined at x equals 0. Natural log of x is not defined for values of x less than or equal to 0. So it's improper, which means we need to replace that 0 value with a dummy variable. I'm going to call it a again, and we need to go to 0 from the right because the 0 discontinuity is at the bottom of our limits of integration. Now we can go ahead and do what I think a lot of you did on exam 2. By the way, this is a quiz problem. I think this is like quiz 7. If you want to go back, no, maybe it's quiz 8 actually. For my section, this is quiz 8. I'm not sure what it is for Dr. Hamidi's. And then this was an exercise on exam 2. Okay. All right. So some of you did integration by parts, but you did not do it with the limit. And because you went ahead and anti-differentiated without acknowledging that this was an improper integral, you lost a lot of points as a result of that. So make sure that you are replacing points of discontinuity or lack of definition before you anti-differentiate. Okay, so if you do integration by parts, I'm not going to show that to you. Some of you already did it, but integration by parts will give you this expression. Then we're going to go ahead and plug in our limits of integration a to 1. So this is 1 squared over 2 natural log of 1 minus 1 squared over 4 minus, now we plug in our other limit, we have a squared over 2 natural log of a minus a squared over 4. Okay. And we can simplify this a little bit before we take the limit as a goes to 0 from the right. First of all, this first term goes to 0 because natural log of 1 is 0. Then we have a negative 1/4. All right. Minus a squared natural log of a all over 2 plus, well, we can actually go ahead and take this limit as a goes to 0 from the right, no problem. This is 0 squared over 4. Okay, so it is left for us to compute this limit as a goes to 0 of this expression a squared natural log of a over 2. And some of you just said it was 0, and that's not good enough. There's a lot to be said here because natural log of 0 does not exist. So what we need to do instead is we need to take this limit. Let's do a little side computation here. We need to take this limit all by its lonesome. And when you get something like, let me put this in parentheses, when you get something like 0 times infinity, which is what you get, I guess, negative infinity, that's a signal for you to want to use L'Hopital's rule. But remember, you cannot use L'Hopital's rule until you get infinity over infinity or 0 over 0 behavior. So that means that if we rewrite this, we can hopefully get that 0 over 0 or infinity over infinity behavior. So I'm going to leave natural log of a up top, and I'm going to move a squared to be in the denominator of the denominator. So we've just rewritten this expression using some algebra trick, but now see that this goes to minus infinity as a goes to 0, and this goes to positive infinity as a goes to 0. So now we're allowed to apply L'Hopital's rule. There are 2 other conditions you should definitely check. They are valid though. So L'Hopital's rule says, hey, you can anti-differentiate the function on the top. The derivative of that with respect to a is 1 over a, and the derivative of the denominator with respect to a is negative 4 over a cubed, right? Okay. So then reducing this just a little bit, you would be taking the limit as a goes to 0 from the right of negative a cubed over 4a. And canceling the a cubed and the a results in a squared in the numerator. So this does in fact go to 0. Okay, but if you did not show any of the work between that limit and 0, you didn't show any of this work, I think you lost 2 or 3 points on the exam. So that's really important. You can't just say that something like this is 0 and not show us why. Okay, but what that finally yields is that the integral that we were trying to compute does converge because this limit in yellow goes to 0. That third piece, 0 squared over 4, is 0, and you get a convergent value of minus 1 over 4. All right. Okay, so this converges, another example, just to drive this home, of a improper integral that converges. So being improper does not mean that you diverge. Here's my last example. The integral from 0 to infinity of 1 over 1 plus x squared. And immediately, because there's an infinite limit of integration, it's improper. We still have to be kind of careful because we do have an x value, not a limit of integral, it's a limit of integration. Because we have an x value in the denominator of our function, we do want to make sure that it's never going to be 0. Is that ever 0 for any x value in the interval? No, never. So this is never 0, so we don't have any other parts of this integral that we need to adapt. We simply need to replace infinity with our dummy variable, b. And we want to take b to positive infinity, and now we leave everything else alone. Okay, so now that we've replaced infinity with b, this function, 1 over 1 plus x squared, is continuous on the interval 0 to b. Because it is continuous on that finite interval, we are allowed to go ahead and apply the fundamental theorem of calculus. And if you'll remember, the derivative of arctan is 1 over 1 plus x squared. So we've applied that. Okay, that's by the fundamental theorem of calculus, but you can't do it unless you've replaced your bad variable with a dummy variable. So we are taking the limit as b goes to infinity, plug in your limits of integration, arctan of b, arctan of 0, by the way, is 0, so I'll just write that there. Okay, now arctan of b as b goes to infinity, let me remind you that the graph of arctan, it looks like tangent, but inverted across the y equals x axis, and it has horizontal asymptotes at positive pi over 2 and negative pi over 2. So the limit as b goes to infinity of arctan of b is pi over 2. So this is a finite value. That means that this limit exists, which means that our original integral, 1 over 1 plus x squared dx, is equal to that limit, which is equal to this finite value. So it converges despite being improper and despite having an infinite limit of integration. All right, so I just hope that those 3 examples really drive home the fact that an improper integral could converge. It could converge. And if you're going to show that it converges, you've got to replace those bad limits of integration with a dummy variable and take a limit. Okay, now we're finally on to sequences and series. And I just want to remind you of some of the tools for testing series, okay? And remember that if you start off with a series, I'll write it like this, okay? Here's the chain of events. Your series could either diverge or it could converge, okay? And there are a variety of ways for you to check this depending on what kind of a series you're looking at. So you can always test for divergence regardless of the series by checking if the limit as n goes to infinity of your terms is not 0, okay? Just because it is 0 doesn't mean that it converges, such as like the harmonic series 1 over n. That still diverges even though its limit does go to 0. But to test for convergence, let me go ahead and erase this. But if you have maybe an alternating series, right? If your series is an alternating series, you can use the alternating series test, and that can only tell you if something converges. Unfortunately, the alternating series test failing is not a dead indicator that a series diverges. So I do want to make that very clear. Okay, you might have a geometric sequence series, okay? And here you simply test the common ratio. And the common ratio being less than 1 does mean that it converges, but you can get divergence if it's greater than or equal to 1, okay? What else can you do? Well, maybe you're not in one of these nice categories of series. Maybe you are, I'm going to do something crazy. Woo. Maybe you're just kind of an odd looking series. There are other tests that you can do. You can always do the ratio test, regardless of your series. You can do the ratio test. You can do the comparison test if you can find somebody to compare to. This is especially nice to compare to P series, right? 1 over n to the p, if you can make a comparison, that's always a nice thing to do. And depending on your series, there's an extra condition here, you could use the integral test. So let me just add what's required here for the integral test to be applied. Ratio and comparison tests can be used whenever. The integral test has to be used in a specific case, and this is the case where all of your a sub n's are positive and decreasing. Okay. All right. Cool. So any one of these tests, the ratio test, if you'll remember, you take the, I want a different color. You take the limit as n goes to infinity of the ratio of your series terms. Okay, let's call that some number L. And we know that this diverges if L is bigger than 1. And we know that this converges if L is less than 1. And it's inconclusive. It's inconclusive if L equals 1. Okay. Comparison test can lead to convergence or divergence. Okay, it can give you both of those answers. And the integral test can tell you about convergence or divergence. So I basically just wanted you to see that one of the only times where you aren't told about divergence is in the alternating series test. The alternating series test does not lead to a conclusion of divergence ever. So just be aware of that, okay? Okay, that's kind of a weird diagram, but maybe we'll come back to it. All right, so let's do some exercises here. So the first question is, determine how many terms of this series are necessary to approximate its value within 1/10,000th of its actual value. The first thing that we want to note is, hey, this is an alternating series, okay? And in my video on alternating series, you just want to check that the part of the series that is, let me call this B sub n, actually. The part of the series that's not got the -1 is always positive, and that's true. Okay, so you do have an alternating series, and this alternating series converges because the limit as n goes to infinity of your non-1 terms is 0, and your sequence of series terms is decreasing. Okay, so it converges by the alternating series test. So that means that there's some finite value, S, that represents the value of this infinite series. Okay, and it's hard to compute this, so the best we can do is approximate it. And if we want S sub n, we want to find n so that the partial sum S sub n and the actual value are less than 0.0001. It suffices to find n so that this B sub n plus 1, or I guess it could be A sub n plus 1, whatever you want, A sub n plus 1 is less than 1/1000th. And A sub n plus 1 is 1 over the square root of n plus 1. Okay, I'm going to solve for 1 over root n plus 1 being less than 1/10,000th. I can divide 1/10,000th over, and I get 10,000 on the left-hand side, and I need that to be less than the square root of n plus 1. So basically we just cross-multiplied that inequality. And then if I square it, I need 10,000 squared to be less than n plus 1. So I need n to be bigger than 10,000 squared plus 1, greater than or equal to. Great. Okay, so that's just the alternating series test error. All right, now we're just going to go into, maybe I'm going to highlight this. This was an alternating series. Alternating series. Okay, now we're going to go into basically just a random smattering of series. And this is probably more like what you'll see on your exam. You're going to be handed a bunch of series. We're not going to tell you what they are. And you're going to need to identify if they are geometric or alternating or p-series, and then try to figure out what tools you're allowed to use, kind of following this diagram. What tools are you allowed to use for that series to test convergence? All right. So this first series, I'm going to say it looks like a p-series, but not quite. So what if I look at its terms? Can I make a comparison of this term with another series terms? Well, sure. What if I just get rid of that -1 in the denominator and leave the numerators the same? So if this thing's numerator is smaller, that means the whole term is bigger. So that's why that inequality goes in that direction. And these terms, because n is never 0, these terms look like 5 over 2 times 1 over n. Well, 1 over n, it diverges, and 5/2 is just multiplying by a constant. So multiplying by 5/2 is not going to make a divergent series converge, right? So let's write that. So 5/2 times the harmonic series diverges, and therefore by this inequality, we have that this series diverges. Okay, and that's what we'd want to see on your exam, just to be crystal clear. That much explanation is definitely necessary. Okay, part B. Again, this series looks like non-alternating. It looks kind of like a P series, but we've got some stuff in the denominator that is keeping it from having a single value of n to a single exponent. But if we throw out, let me copy this term. If we throw out positive terms in the denominator, that's going to make this thing bigger, right? Because those positive terms in the denominator, are making the whole fraction larger. Sorry, these positive terms make it smaller because you're dividing by something that's bigger. All right, that's confusing, but I think you understand what I mean. So this is 3 times n over, well, n to the 5th square root is n to the 5 halves, and that reduces to 3 times 1 over n to the 3 halves. Okay, now 3 times a convergent series, by the p-series test, that converges, right? And so by our inequality that says that our series terms are less than this convergent series terms, let me copy my less than inequality with the blue circle. Our series that we started with must also converge. Great. Okay, so let's just identify the two tools that we just used. We started off with a series. What were those two series, alternating or geometric? No, they weren't. So if we're going to test for convergence, we could have first actually tried and to check and see if the limit of our sequence terms went to 0 or not. Turns out both of them, this sequence, let's just look at the sequence without the series, that sequence goes to 0. So because it goes to 0, we don't know if it diverges. That is not a conclusive test. Same thing here. This sequence without the series also has limit as n goes to infinity of 0. That doesn't tell you anything. If it didn't go to 0, that would tell you something. But since it doesn't go to 0, we've got to go back up here. This pathway is not a valid pathway. It's not an alternating series, so we can't use the alternating series test. It's not geometric, so we can't take that pathway. And its limit as n goes to infinity of the sequence terms was 0. So the only pathway we have is to go and try one of these convergence tests that is valid for any series. All right, so I hope that line of thinking is clear and useful. All right. Okay, so this next series, hey, it kind of looks like a geometric series. So let's write down the terms that are being added up. This is a sequence, right? We'll call this a sub n. This sequence can be compared to, let's make it smaller by getting rid of that -1 in the denominator. Okay. And we can make it smaller by taking away that +1 in the numerator. Okay, well now we have a nice sequence whose series we can say something about. So this series, 3 halves to the n, okay, this thing is geometric. I don't have it written in its geometric form, just to be very clear. Here's what that would look like. We'd pull a 3 halves to the front. That would be its a value, and then 3 halves to the n-1 is the common ratio. It's geometric, and it diverges, right? Why does it diverge? Well, because its common ratio, 3 halves, is strictly bigger than 1. Therefore, by the comparison test, our original series must also diverge. Okay. All right. hopefully we feel okay about that. So we just use the comparison test in all three of those. We can use the comparison test for part D as well. Maybe I'm feeling crazy and I'm going to try the integral test. Okay, so remember that your sequence terms need to have an affiliated function. What would our affiliated function look like? It would look like 4 over x times x plus 3. And that affiliated function needs to be decreasing on the interval 1 to infinity. And it is, okay? So this is decreasing on the interval 1 to infinity. And it's positive. All of its values are bigger than 0 on that same interval. So that means we can use the integral test. And we don't have to. There are actually options here. But the integral test applies here. So basically, we were still in the scenario where none of these paths are valid. We have to take this path. And we have 3 options. Okay. So I'm just using the integral test because I can. There might be other ways to do this, like the comparison or ratio tests. So the integral test says, actually the ratio test would be inconclusive, and maybe you should try that out. But the integral test says, hey, if this integral, 4 over x times x plus 3 dx, if this converges, then our series converges, right? Well, that is true. This integral does converge because, well, we're kind of doing another comparison, aren't we? Because 4 over x times x plus 3, that is always less than or equal to 4 over x squared, which we know its integral converges. This guy's integral from 1 to infinity converges. So we just use the integral test with a comparison to another function whose integral converges. Okay, all right, so this guy converges. Cool. All right, so I think that maybe what would be useful, I mean, do what you want, but what might be useful is for you to try to use the ratio test here. Try another test. I know that this can be compared to a geometric series to show that it diverges. You might also try the ratio test just for fun. You should try the ratio test here as well, and you can see that it will be inconclusive here. Oops. The ratio test is always inconclusive for p-series or things that are close to p-series. All right, so that might just be a good exercise for you to try. All right, problem 4. So this is getting into the categorization of series. And if you'll remember in my alternating series video, I drew this Venn diagram, and I'll draw it again, but it's basically, let me come up here, it's basically following these 2 branches of diverge and converge. So I'm going to make it maybe at the bottom here. If you start with the series, it either diverges or converges. Okay, now if it converges, it is possible that the series made up of the original series but with an absolute value, this could diverge or converge. Okay, so if your original series converges, then you could go so far as to ask if this new series converges or diverges. And if you are along this path, you just say it diverges. If you are along this path of converging, then you either converge, but your absolute value series diverges, in which case you would be called, your original series is called conditionally convergent. It only converges without the absolute value bars. Or you're in this other case where your absolute value series also converges, and this is the nicest possible setting where you are what's called absolutely convergent. And that's the original series that's being called absolutely convergent. Okay, so hopefully you see that flow chart. Let's go back up. So let's just see, first of all, if you absolutely converge, then you conditionally converge. So let's test for that first. So this series from n equals 1 to infinity, from negative 1, n equals 1 to infinity, negative 1 to the n over root n, is absolutely convergent if this series with absolute values around it converges. So let's look at that series. This series from n equals 1 to infinity, if I take the absolute value of the numerator, I just get a 1 because negative 1 to the n is positive 1 if I take an absolute value, and root n is always positive. Well, this is a p-series, and the power of n in the denominator is 1/2. So this thing diverges, okay? So because this series diverges, the original one is not absolutely convergent. It could still be conditionally convergent, and that's what we need to check. So the original series, it's an alternating series, right? With the positive part being 1 over root n without the negative 1 to the n. So it's alternating, and so we can use the alternating series test, which says, hey, does the limit as n goes to infinity of 1 over root n equal 0? Yep, that's true. And is it decreasing? Is every subsequent term smaller than its previous term? Yeah, that's totally true because the denominator root n plus 1 is bigger than the denominator of root n, so the reciprocal inequality holds when you take the reciprocal of that number. Okay, so that says that this series converges. Well, what does that mean about if it's absolutely or conditionally convergent? It's conditionally convergent. Okay, it is only in this yellow category in this little flow chart. All right, the other one is an alternating series, again, but let's test if it's absolutely convergent first, because that might actually tell us if it's conditionally convergent without us having to test, okay? So this is absolutely convergent if, I'm not saying that it is, but it would be if we knew that the series with its absolute value converges. Okay. Now, as we look at this series, this is a brand new series. What is it? Is it geometric? No, it's not geometric. Is it alternating? Nope, not alternating. Does the limit as n goes to infinity go to 0? This limit's actually kind of hard to compute. So I can't even tell, but what we can do is we can follow this left path here, all right? Follow this path because I don't know about that, but these are no's, no and no. Okay, so we're going to follow this path, and I feel like doing the ratio test. Anytime there's just a ton of clutter, the ratio test is really nice. So let's try that and see what we get. Okay. So the ratio test wants us to take the limit as n goes to infinity of a sub n plus 1 compared to 1 over a sub n. So I'm just going to write its reciprocal here. N to the 100, 100 to the, nope, that's not the reciprocal, that's the original. So the reciprocal of a sub n is n factorial over n to the 100 power times 100 to the n power. Okay, so as usual with the ratio test, when you compare these terms, you get a lot of cancellation. So we're going to have the n plus 1 to the 100 and the n to the 100. Again, I think I've warned you like 1,000 times. Do not, under any circumstances, cancel those. They do not cancel, okay? We do have n plus 1 100s in the numerator and n 100s in the denominator. That leaves 1 100 in the numerator. And then the n factorial in the numerator and the n plus 1 factorial in the denominator leaves us with an n plus 1. Oh my goodness. Okay, so what's going on here? This numerator has degree 100, right? If you were to FOIL n plus 1 out, you would have n to the 100 as the largest power of n. Whereas if you FOILed this through, you're actually going to have a term of n that has degree 101, right? All right, so that means if you take the limit, you get 0. And the ratio test says, all right, well, 0 is less than 1, so this series converges. That means that what we just tested for was the absolute value series. The absolute value series converges. Oops, I'm transposing, sorry, the terms. But this absolute value series converges. So the original series the original series converges. Absolutely. Because when I took the absolute value of its summand terms, those converge. Okay, so we are over here with that particular series. Okay, so I hope that helps you see how you can determine if a series is conditionally or absolutely convergent. Of course, if it's divergent, you don't even need to go there. Okay, all right. So now we're going to get into some application problems that I think are just really cool for applications of series. And the two applications that we have are actually going to be like geometric examples, but I think they're super cool. So the first problem is, imagine you have like a bouncy ball or basketball or something, and you drop it from 10 feet up. And every time it bounces, the next time it goes up in the air, it only reaches 70% of its previously reached height. Okay, so let's define a sequence, a sub n, whose terms are actually telling you what that height is. So I'm going to call A0 10 just because that's where you dropped it from. But then what's 70% of 10? It's 10 times 0.7, which is 7. What is A2? It's 7 times 0.7 because it's 70% of 7. That's 4.9. And then A3 is the previous height, 4.9 times 70%, right? Okay, so I'm not going to compute that, but are we seeing a pattern? Well, yeah, we could say that A4 would be 7 times 0.7 cubed because we've multiplied 7 by 0.7 3 times at this point. So the pattern here is that the nth time the ball bounces, it will be 10 times 0.7 to the n minus 1. No, it won't. It'll be 7. Sorry. There we go. Okay, excellent. Or alternatively, maybe I could say 10 times 0.7 to the n. That's equivalent, but either way, let's use this one, okay? All right, so what is the total distance traveled by the ball after 9 bounces? Okay, let's just write out a couple things here, because the first time the ball falls, it travels 10 feet, right? Then when it bounces, it comes back up 7 feet and it has to fall that same distance. Then the next time it bounces, it travels upwards 4.9 feet, then it has to fall that distance. So if this continues, what we've got is a naught, the distance it falls the first time, plus twice the height it reaches on its second bounce, plus twice the height it reaches on its third upward bounce. And we just keep doing that, right? All the way through the 9th bounce. Okay, so instead of calculating all of that, let's write this as 10 plus 2 times, what is a sub 1? Well, we already said that a sub 1 would be 7 times 0.7 to the 1 minus 1, plus 2, here's a sub 2, 0.7 to the 2 minus 1, etc., until we get to 2 a sub n. A sub n would be 7 times 0.7 to the 9 minus 1. Let me write that as a series because we've got a lot of repetition. So that last part looks like the sum from j equals 1 to 9 of 2 times 7 times 0.7 to the j minus 1. All right, and we derived this all the way back in 10.2, okay? This series that we just wrote down, it's a finite series, okay? Series can be finite or infinite, but it is a finite geometric series, which means, I don't know if you remember this, but we do have a formula for the sum of finitely many terms in a geometric series, and it looks like this. A over 1 minus x, that's what we're used to, right? But then there's an extra 1 minus x to the n. Okay, so we've got 10 plus our a value. Here it is. What's our x value? Here it is. So we've got 10 plus 14 times 1 minus 0.7, n is 9, all over 1 minus 0.7. So that's the sum formula for a finite geometric series. And I think when you reduce everything, you get that this is approximately like, actually I have equals, maybe it actually reduces perfectly to this, 46.198 feet. Okay, so what was cool about this? First of all, we built a sequence, and you should be able to do that. Given a life-like scenario, you should be able to build a sequence that represents some measurements in that scenario. And then we built a series to add up the terms in the sequence you developed. Unfortunately, your textbook doesn't have very many examples of these, so Dr. Hamidi and I thought it would be important for you to see some examples like this. Problem 6 is super similar. You've got I don't know, I was just imagining a ladybug hanging on for dear life here, but sorry, I had a lot of fun writing this problem. Okay, so we've got a ladybug. It's chilling. I apparently made some adaptations to this worksheet, and I'm going to have to change them back. So this, I actually want this to be 5. I want this to be negative 15. If you look at the solutions are correct. So I apologize. I want this to be 15 over 2, negative 15 over 4. I'm just going to cross those out, and we'll deal with them. So you got a ladybug. It's hanging on to a spring. So here's my spring. And then I've got a ladybug that's having a hard time because it's just trying to relax or whatever, you know. Okay, it's just trying to relax. But basically, you come along, you terrible person, and you extend the spring 10 centimeters past its natural length. And when you release it, of course, the spring is going to bounce. So the question is, I want us to define a sequence, capital S sub n. By the way, that should lead you to believe that we're actually building a sequence of partial sums instead of a sequence like we did in part A, whose terms give the distance the ladybug has traveled after n oscillations. So this is kind of more, let me just say, this is more like part B of problem 5 than it is part A of problem 5. I just want you to recognize the difference here. Okay, so let's do this. So the first oscillation I'm imagining is just you extending the, it's just you extending the spring. And I've got this great picture. I kind of think I'm going to go grab it instead of redrawing it here because it'll just take too long. So let me copy this. Copy. And here we go. Okay, cool picture, huh? Yeah, I think it's pretty nice. So, great. So basically, the first time you pull the spring down, you've pulled it 10 centimeters past its natural length. So I'm going to count that as a 10 centimeter oscillation. And then once you release it, right, it travels past its natural length all the way down to have only 5 centimeters of length. 5 centimeters of length. Well, if it's 5 centimeters long here, it's actually gone 15 centimeters past its natural length, right? So far it has traveled 10 centimeters plus 15 centimeters to get up there, and now it's going to have to come back down. Okay, so it had to travel up and then back down, so it's got another 15 centimeters it will travel. What is S2? S2 is everything that's already happened, right? You've already traveled that distance, and now we're going to count how much distance is traveled in the next oscillation. Well, in the next oscillation, I want you to use 15 over 2 here. You travel 15 over 2 centimeters down, but then you have to travel back up to get back to the natural length. So this is 15 over 2 plus another 15 over 2. Okay. All right, just maybe for finality, we so far have traveled that distance. Now we're going to add on the next distance that we travel is 15 fourths, and then we have to come back 15 fourths. So hopefully you're starting to see a pattern here. We've got that after n oscillations, if you return to the natural length, you had an initial 10 centimeters traveled, but then you had 2 times whatever length was being traveled. And it looks like that length is 15 over 2 to the n minus 1. And you can just check that that formula works out, right? Because, oops, there should be a sum. See, I did it again. I treated it like it was 5A instead of 5B. So you've got terms that look like 2 times 15 over 2 to the, let's say, j minus 1, but you're adding all of those up. Okay, great. So that is our formula that we're going to use for the partial sums. And now I ask you, how far has this thing traveled after 15, not 10, sorry, my solutions, I just want this to match, 15 oscillations. So what are we finding? Well, we're finding S sub 15. And instead of you having to write this out another 12 times, we're going to use our geometric series formula for finite geometric series. So this is 10 plus, let's make sure this is in perfect geometric series form. We start at 1. We go to 15. Our A value is 30, and we have 1/2 to the j minus 1. Now that's in perfect geometric series form. Our common ratio is sitting right there. There's your x. Your A value is right there. It's 30. And our finite sum for geometric series is, again, A times 1 minus x to the n all over 1 minus x. Our A value is 30. Our x value is 1/2. The number of terms we're adding is 15, all over 1 minus 1/2. Okay, and this comes out to be 817 centimeters. Okay, and I know this problem isn't asking for this, but let's just suppose that the spring is like in outer space. So the spring constant is slowing it down. It's making it oscillate less and less of a distance, but otherwise it would just keep oscillating. It would never come to rest. It would just oscillate at almost imperceivable small little distances. So what is S? Yeah, like what if we just let this thing keep oscillating forever? How far would that ladybug travel? It would travel 10 plus our sum from j equals 1 to infinity, 30 times 1/2 to the j minus 1. Well, this is 10 plus, this is now an infinite geometric series, so our formula is a over 1 minus x. So this would be 10 plus 30 all over 1 minus 1/2, and that is 10 plus 30 over 1/2 is 60. Whoa, well that's crazy. So basically after 15 oscillations, the ladybug's already pretty much traveled as far as the spring is going to travel if it just goes on forever. So that's why spring's oscillations are pretty much imperceivable, despite the fact that that vibration is still occurring. It's just slowed down to such a small amount that you can't even really see it. Okay, thanks for watching. I hope this is helpful for your homework and for studying for quiz, the next quiz. And please let me know if you have questions.